Okay, for another example, I've got the function f of x equal to x to the 2/3 power plus 5. Notice the domain of that function is all real numbers. I'm taking the cube root there and squaring it, so I can do that with any real number, and then added to 5 is going to give me a value for any number x that I put into that function. It's going to give me one and only one value back for all real. So the domain is all real numbers, and I want to investigate where this thing is increasing and decreasing, and also want to determine if there's any extreme values. So I'm going to take the first derivative. I have 2/3 x to the minus 1/3, and then the derivative 5, of course, is 0. So I'm going to write this as 2 over 3, and x to the 1/3 in the denominator is the cube root of x in the denominator. I'm also going to set that to 0 and determine if I have any critical points. This is a fraction, and the only place this fraction would be 0 is if the numerator is 0, but the numerator in this case is a constant 2, so the expression on the right will never be 0. However, there is a critical point. The derivative doesn't exist at x equal to 0. I can't divide by 0. Now, the original function exists there, but the derivative doesn't, and that turns out to be a critical point. I'm going to take a couple easy test points there and determine where this function is increasing and or decreasing. If I put -1 into the derivative function, then I would get, actually the cube root of a -1 is negative, so 2 over 3 times the cube root of -1 would be negative. That's all I need to know. So all the values in the interval from -infinity to 0, the original function f is decreasing. And if I put 1 in there, I'm going to get a positive derivative, which means the original function is increasing from 0 to infinity. That was my only critical point there, was 0. And the function exists on all real numbers, the domain. Now, do I have a critical point that produces an extreme value? Well, the derivative is decreasing and then it's increasing, so I have a relative minimum at 0. So at x equal to 0. 0 is in the domain, by the way, so this value exists. At x equal to 0, there is a relative minimum because the derivative goes from negative to positive. In other words, the function's decreasing and then it begins to increase. The minimum is, well, it occurs at x equal to 0. So at x equal to 0, the minimum is f of 0 equal to 5. The minimum is 5. Now it's interesting, in this problem, as opposed to the last problem, I had the derivative being 0 at both -1 over the square root of 3 and 1 over the square root of 3. Derivative being 0 means there's a horizontal tangent line. But in this case, this critical point was a point where the derivative didn't exist. And the derivative doesn't exist at functions where there's a sharp point. That's one possibility anyway. If I graph this function, 1, 2, 3, 4, 5, 0, 5 is a point. The function is decreasing to that point, and then it is increasing. So if you have a graphing calculator or you graph some points on this, you'll see that it is a curve that comes to a sharp point and kind of goes off from the vertical axis, like similar to this. So if you plot the points there, you can see I've got a local minimum at 0, and that local minimum is 5. And it's a sharp point on the graph. And I suspected that because the derivative doesn't exist there. Although it still can be a relative extreme value.